Okay, this topic is about devices. So, a device as we define it in this logic is it's really a component that comprises inputs, outputs, but basically it's like a mechanism or a section of the robotic work cell which you could consider its own entity. So examples of this would be the robot, deburr, the washing station, etc. So, first thing that we're going to look at with devices, talk about device states and behavior. And we'll go through and look at the state machine for a generic device. Then we'll look at the interface. So, how do we communicate back and forth with that device within the logic? And then I hope to talk about fault triggering, monitoring, reaction, and clearing in this discussion as well. And then I plan on uh, demoing how to add a new device into our system. And so I would like to demonstrate that with our wash device. So with that, we'll talk about our primary device state. So the a device is really a collection of states and I guess the idea behind a device is that, yeah, if we use a consistent state um, definition, that when someone tells us, hey, this device is idle, this device is running, this device is inactive, faulted, killed. When someone says that, we don't really know how the code works behind the scenes, but we have a general idea of, what is this, what assumptions can we make about that device without having known anything about the logic behind it. And so by keeping these device states consistent amongst all the different devices within the cell, um, we create a common language between different um, device modules, and so that drastically will improve and help understanding how the whole system itself works, as long as you kind of abide by these different states. So um, I think the best way to maybe describe the states is I'm just going to walk you through a typical state machine for a device. And so all of the devices follow this actual state machine. So um, the state transitions are all consistent between any of the states that employ this device state machine. So immediately when we first power on the machine, we enter into a boarding state. So in a boarding state, generally, we're trying to kill all processes and disable all motors, drives, actuators, outputs, anything that might be hazardous. Generally, that's what we're doing in aborting. So we're killing ourselves, and then we're also killing our children. um, just talking out loud. It sounds kind of sadistic, but anyways, so the idea is while we're aborting, we kill ourselves, we kill our children. Before we move to a killed state, we verify that everything is in fact dead and all of the children below us are dead. So when we finally do transition from aborting to killed, and you see that a device is killed, you can assume that it's basically de-energized. It's not doing it's not doing anything. So if a device happened to contain something like a motor drive, you'd want to disable that drive in this state. So we do this at power up. We also do this um, whenever we issue a kill command to the device. Um, Typically, a kill command is going to come whenever an e-stop is triggered. Most of our devices are dependent upon the e-stop circuit, as its um, energy provider. Most of the devices run off of the e-stop circuit. Their energy is derived from electricity that's powered from the e-stop circuit or air that's coming from the e-stop circuit. So in our system, when you hit the e-stop, it kills the air supply, it kills the any of the control power to the outputs, drives, things like that. So without the e-stop, basically you can't run a system, you can't run a device on most devices. So that's why we transition to aborting, and then we go to this killed state. And so we sit in this killed state until the kill command is released. So, for example, if our parent was killing us, we would go to this aborting step. We'd kill ourselves, kill our children, verify they were dead, then go to killed state. And then our parent would see, oh, okay, the device is in its killed state. Then it would relinquish its kill command, and it would itself go to a killed state. And so you kind of see how the chain reaction would occur up and down the line. So once we're out of the killed state, we sit in an active state. There we would either we can go to a faulted state if there are errors present in the device. So if we triggered any errors at all, we would sit in a faulted state, wait for them to be cleared. Once they're cleared, go back to the inactive state and wait to be reset. So it's assumed that in a killed and an inactive state that we're not doing anything. We're the device is not it's not doing anything. It's basically inactive. um, the killed state is a special case because we're like holding it in this killed state, until we deem that it can be reactivated. So we'll typically hold ourselves in a killed state as long as the e-stops are active. So when we want to start running a machine, we want to start running a device, we have to then go through a resetting step. And in a resetting step, we're doing things like initializing data, initializing outputs, all kind of based on typically on either the part data or some sensor information. But effectively, we're getting ourselves ready to be run. So once we are finished initializing everything, we sit in our idle state. In our idle state, typically we're ready to go. So if we've got a motor drive, our drive is enabled and active and ready and waiting for commands. So in idle, we're really just waiting for someone to tell us to start doing something, start a command, do a task. So there's kind of a list of kind of just generic commands that a parent gives to a child, and so you can kind of see those commands are in that gold font. But once we're in idle, we get the start command, then we transition to running, and we do whatever logic is in our running logic. And in running, there's like one of three things that could happen. So somebody could pause us, and in most of the time, and I think in this particular machine, we're not really using this feature, this pause state. It's not really something that we're using a lot of. I think the only place we kind of use it is in the CNC program logic, because we allow the operator to pause the NC program execution. But most of the other devices, it doesn't really ever use the paused state. So the other two options are, well, I guess there's three more. I lied. So someone could issue us a stop command. So in a stop command scenario, sorry, I realized this should say stop. So in a stop command scenario, we transition to the stopping state. In a stopping state, generally we are stopping or killing, stopping or turning off some of our outputs, In the motion control aspect, you would tell a robot to stop moving or tell a motor to stop moving in this transitional state, the stopping state. And then once you have verified that everything has stopped or stopped processing, then you basically transition back to idle. Now, if we happen to encounter an error while running and we transition to stopping because of that error, then we would take ourselves through the aborting step and then basically wander our way through the killed step and then out to inactive and then finally terminate at the faulted state. So anytime we have an error come up, we need to make sure that everything is, we need to stop all things that need to be stopped and um, get ourselves to an inactive state. So again, letting all the other programmers know, letting the operator know when I'm in an active state, nothing's moving, nothing should be active. It should be, dormant, or it, should really be inactive. So the other outcome from the running step, obviously, is we finish the task successfully. And so in that case, we transition to kind of a done step. So in the done step, we're not doing anything other than just waiting for our parent to drop the start command or drop the task command, whatever it might be. But generally, we're sitting in done until that start command drops. Once the parent sees we're done, they'll drop the start command, and they'll wait for us to transition back to idle. So once we're back in idle, we can then successfully get a newly issued start command. So you can see if we don't wait for that start command to drop, you can see we would just slingshot back into running and we would never stop. So that's why we're waiting for that start command to drop. And that's effectively the basis for the state behavior. So like I said, anything up from like the conductor down to like the FANUC controller devices, all those all those devices utilize this device state machine, and they utilize these different states, and they all effectively have the same meaning. So when we want to communicate with a device, there is an interface by which we use to govern govern our commands and control our commands and to exchange data between a parent and a child device. So the idea is with a device interface, we really want to constrain the amount of information that we're sharing about ourselves to the parent or to the world, and we're minimizing, or we're giving a known procedure for how to issue commands. And so the way that we do that is every device has a data type, and within that data type structure, there is something called a commands data type. So typically your parent writes to that commands data type, and that's how it's issuing the start, stop, reset, clear faults, whatever it might be. All those commands are housed in that data type. So that's a really prominent interface data type for command delivery from a parent to a child. And the commands data type is generic. It's common to all device types. So not every device is a one size fits all. They're not all the same. So in order to enable some customization between devices that may have the need for custom commands, we have something called handshakes. So in a handshake, effectively you have a request bit and then a done bit to complement the request bit, but effectively um, the parent device would set the request handshake bit the child device would react to that request. It would perform the duty. And in a lot of the cases, I believe we're issuing a change recipe request, and then the child device updates the recipe, says it's done updating the recipe, and then the parent would then drop that handshake request. So those are like the primary methods for issuing commands from a parent to a child. And then in a child device, obviously the child is updating its states. It's relaying that state information back to the parent and to the world. Also, its errors. So if it has any errors present, it's letting the parent device know that. Obviously, it's updating those handshake requests with the done bits. And then each device will typically have its own device data structure, its own device data type, again, to allow for some flexibility, between devices that are different. So there may be um, certain data that the world wants to know about for a particular device, and so we basically manage that by creating a custom data type structure and then allowing access to that data type by the parent and by other folks. So the child device is typically writing to that child data structure, and then the parent is just typically listening to the data or just reading it. In certain cases, I do allow the parent to write to a designated um, substructure within that data type. Um, Mainly, I did that because I did that with the robot, and we'll get into that a little bit. But the robot issues um, a task request ID, and it was just more convenient to do it that way rather than doing like a handshake for each and every task request ID. So there is some freedom, some flexibility in how you kind of choose to do handshaking, device data, commands. So the there is some flexibility for the con- controls engineer. They can kind of choose the method that applies best, but I would generally just say, as a rule of thumb, if it's a simple device that just needs to turn on and be ran and turned off, the commands data structure already has a start and stop bit in there. And so that's basically all you would need. You wouldn't really need a handshake, and you'll see that when we run things like the deburr tool and the washer. Um, we don't need any custom handshakes. We just basically need the start command. Um, and then I would say for handshaking, if there is a something specific where you wanted to make a request and then let them know when you're done with that task or something, you could use that boolean paired type logic. But other than that, you could use something like the device data as an interface as well. And I think that kind of concludes the interface section. So fault triggering, monitoring, reaction, and clearing. I might get into the nuts and bolts of this a little bit deeper, maybe when um, well, I guess we can kind of discuss it. So the specific device, as it's rolling along, it will encounter something where it's like, oh, I'm faulted, I need to trigger an error. Once it triggers that error, then there's a couple people listening. One, the parent is typically listening. So if the parent is telling the child to do a task and it's waiting for the child to finish the task, or if it sees it's errored out, then typically the parent will then react to, okay, well, my child has an error, so I need to stop the process, stop what I'm doing, stop what everything else is doing, and then um, the parent will then take itself into kind of a faulted state, and then its parent will react to that as well. So um, with that, that's kind of like the sequence or the chain of commands of which, if you have, let's say, I think the most complicated case would be if let's say a grandparent is commanding a parent to do something, the parent encounters an error. Um, so all the children of the parent are good, but the parent itself has encountered an error. The parent will take itself to a stopping transition, and in that stopping transition, likely the parent will be issuing stop commands to the children. It's likely that the children are probably already stopped or idle, so really once the stopping complete has been detected, then that parent would take itself to the inactive and faulted state, and then um, the grandparent would be reacting as well. It would be likely issuing a stop command as kind of an echo. It'd be issuing a stop command back to that parent device, and then um, once the parent device is done, that grandparent would then take itself to a faulted state. And the children would all just kind of go back to either an idle step or to an inactive step. I believe they would actually go back to an inactive step because ultimately the parent would come through aborting, issue an abort kill command to all its children, and the children would go to inactive. So it might be good to maybe diagram that, but I think, sequence of operation in a grandparent parent child scheme, if the child, and again, this is the most complicated case, but if the parent gets an error, likely the grandparent detects child error and issues stop command to parent, but the parent will likely already be stopping itself. And its children. So then parent stops itself and children and goes to faulted, or actually goes to, sorry, aborting. Parent waits for children to be killed and then goes to inactive, basically. Or, sorry, goes to faulted. And then likely the grandparent would kill itself. I believe that's how it's set up. Basically, everyone's killing themselves in a certain order, though, and then those who don't have faults are inactive, and those who do have faults, like the parent, is in a faulted step, and then it sits there until the operator clears the faults on the HMI, and then everything goes to inactive. Yeah. So let's jump into. Let's look at the actual code. So we looked at this device state machine. So I have a template for that device state machine And if you look in packages, device, and I believe it's under this device function block template, double click on that. This is the sorry, I just want to demonstrate that that's the one there. So we click on that, that one opens up. So this is a device state engine or device state executor. I call it an executor. It's a state machine, but basically this template should be, copy pasted and placed, copy pasted and placed into um, wherever it fits in your source code here, and then you can make your modifications to the um, logic as you need to. So walk you kind of through what are all the components and everything that's in here. So at the very tippy top, we have the configuration. So typically when we look at a device template, we have a few input variables that we're giving to this function block. One of them is a parent ID and an ID. And so we store that information in this configuration function block. Basically, we just set this config data structure. We just give it the correct data in this step. So it's not really that complex. It really only runs the very first scan of the program once it powers on. So yeah, when you look at a device, each device has a device config. So if we go to this definition for a device, here's the substructures. So you see it has this config. So if we go and look at the data structure for config, we have something called the mnemonic, and that's the shorthand notation for the device. So typically, I try to limit this to like 3 to 5 letters. For the CNC controller and the robot controller, I kind of violated that just because they're both FANUC, and I could have probably used a shorter hand notation for them, but anyways, the mnemonic here is actually I need to update that. So yeah, that's stored there. This ID, that's the actual device ID. Child array, this is the children. This is just an array of other device IDs, so the children of you. Right now I have this defined, limited the length of that array as defined in the global constants, global variable, and looks like it's 10. So I can only have up to 10 children, which is probably a good idea. I don't think people need to be having more than 10 children. And parent ID is, what do you think? Your parent. So whoever your parent is. So this is your parent. And again, you pass all this data to that function block from the caller, from the calling function. So for example, in conductor, I have this conductor function block, and I have these children devices at the bottom. When I declare this robot function block device, I pass in the parent ID, which is the caller, in this case conductor, and then I give it the ID, which in this case is the robot. So there may be cases where you might have two robots, so you might have identical function blocks, and maybe the device ID, instead of robot, you have robe1, robe2, and so that's why we're doing it like this. So it just allows you to have that sort of modularity in the code. You can add additional devices that are identical. So kind of looked at that device config function block. It's just assigning that, just copying parameters in and storing it in that configuration data structure. So pretty simple rung there. Now this rung is pretty critical. This one goes at the top too, but this is effectively how we're able to create some of the instantaneous logic, reaction-based logic when we get certain parent commands. So you'll see in our device data type we have that sub command called commands, and so these are your device parent commands. You can see here's the list of different parent commands. These are just like stock off-the-shelf commands that every device has, that has their parent has access to. And so in the device in this device inputs rung, basically I am, one case I'm reacting to this kill command. So this kind of logic right here, this sort of sub rung should be present in almost every single one of your devices. And so it sets this instant kill bit on, and we'll see kind of how that is reacted to in the device state engine. But this effectively is how we achieve this behavior right here. So anytime this kill command is on, we immediately jump to aborting. So it doesn't matter where we are in the logic, if I see a kill command, boom, we're going to jump to aborting. So that's represented here. There's also some other instant stuff. There's a condition for instant reset if we're in the idle step and we get a reset command, will allow us to jump to instant reset. So we'll just go through a resetting routine. Instant stop. Typically, you might do this anytime you have an error, your child has an error, and you are either idle, paused, or running. So we'll kind of look at some of these other substructures as well. But yeah, I guess while we're on that topic of states, let's jump back to the device substructure, this device data type. So every device has this. I have something called device status, and this one's pretty crucial. So this is how the parent or anyone in the world knows what the device status is. And typically, we have this device state. So this is an integer value, and we use an enum to kind of look up. So we say, okay, what state are we in? We got an enum for that. We got a step number, typically representative of the state, but not necessarily. This color code is really for HMI purposes. Then we have Boolean states. So these kind of echo this enum. And sometimes in the logic, it's just easier to do like a Boolean logic analysis, like is idle, rather than doing like an EQU dev.is.state equals states.idle. This is just a little more compact, a little bit easier, a little shorter, but effectively, this is just redundancy of this and vice versa. So this and this are generally the same, and we'll see that how that occurs in the device in the state engine. So it's all pretty much handled for you, but we add that in there just to give ourselves easy access in our logic. Then I have some like special states, like sometimes the parent will react to certain logic if I'm faulted or idle, if the child is faulted or idle. kind of combine those two states, so it's an or. Same thing with this IIFKM, idle or inactive or faulted or kill or manual. So you get the picture. So there's a few of those that are in here. And again, if I just hover over these data types, you can see, like, I don't know what IPR means, but when I hover over it, it's like idle or paused or running. So it's, it's pretty convenient to do that here. Okay. So every device that you have has this dev data type, and you actually pass it in. Um, so this typically, all the device data types, they all exist on the main. Um, yeah, so this device data type, again, has all this information. We've got the parent commands. So the parent writes to the child's um, device command substructure. HMI commands really is not being used in this particular machine, but in like previous projects, it's typically that's how I would enable someone to control the machine in a manual mode type aspect. I would have some HMI command push buttons for that associated device, and the operator could kind of like selectively hit those. Then we have this errors data type. And errors, really, you have a list of errors. It's a list of fault data. Fault data is basically just an error code, device ID. Yeah, there's some other stuff in here I added, but basically the big hitters are kind of these two things, really the code. And then this present bit. So anytime when this list populates, so a device can have several active errors at once, and so I defined, I think I limited that to 3. Yeah, so I'm not recording more than 3 active errors at once. If you're triggering a shit ton of errors in your logic, then you may be confusing the operator. So you might want to rethink um, how many errors you allow yourself to trigger at once. Um, so that's why that's limited to 3, just to kind of reinforce um, that mantra, that mentality. Then we have this present bit. It's the status bit. This is really typically used by the parent. The parent's looking to see if the child has any errors present. If they do, and they react accordingly. And then we have this children's present bit. So this is set by our own logic when we're looking at the children, and we're constantly looking to see if there's any errors. And if any of our children have an error, we set that bit high. So that's device fault data. Exact same thing for warnings. So same thing for errors. It's the exact same data type. Um, and I think I haven't discussed this yet, but the difference between an error and a warning is an error is a non-recoverable fault. It's a non-recoverable uh, event, it, that requires intervention. A warning is simply a notification that something is off, something is not, normal, or something is not running as expected, but we can continue to run the process. Um, it's just you just be aware that there's an issue. And then finally, this device inputs data type. This kind of goes back to those reactions. So this instant kill, instant stop. This just allows ourself to create a variety of cases where not every device is going to be the same. Not every device is going to have the same logic, which will set this instant kill. So I'm giving the controls engineer the option in this rung to determine what conditions should set this instant kill. in some of the cases I only not only react to this e-stop circuit, but I also react to like the fence circuit. Um, so but not every device depends on the fence circuit. Like the robot can run if the fence circuit's not okay, the robot can still run in sort of a manual mode. So there would be a difference between, how the robot would react versus maybe like the deburr tool, for example. The deburr tool is tied to the fence circuit, and so if the fence circuit goes out, the deburr tool basically has to go to a killed state. It has no energy. It has no power. So this kind of this specific rung enables you to create custom logic that will allow your code to set these sort of reactionary states. So do you want to allow it to reset? Do you want to allow it to do a stop, instant stop? Do you want to allow it to go to manual? So um, a good segue to discuss that will come up in our device state engine. So I think I will cut this video off right here, and then I will transition into the device state engine after this.